Hey everyone, Geophysicist Stefan Burns. Yesterday we had an incredible solar storm impact that was absolutely truly epic. It was one of the biggest solar storm impacts that we've had in decades. What we had back in May of 2024 is bigger. That's the Gannon storm. That was a G5 storm. What we had last night was a G5 minus impact. And then the storm decreased in strength. A lot of people have been talking about how what's going to happen tonight is going to be even bigger than what happened yesterday night because of the solar storm lineup. 3 solar storms were launched from Earth center direct towards the planet. And well, if you look at the solar wind data and you actually understand this stuff, it looks like the main impact has already occurred. But that does not mean that the geomagnetic storming is over. We're likely to get a second increase in geomagnetic volatility tonight. In fact, it's basically starting right now. We're going to go into the real-time solar wind data so you can understand. And this is relevant because a ton of people saw the Aurora last night, myself included, for the first time because it extended so far south. There were Aurora sightings even down to Mexico. In Europe, there were some sightings down in Spain. So it went to the southern latitudes, though those sightings, of course, were dark sky conditions, mountaintops where you're above a lot of the maybe clouds or haze, and also long exposure photography, and they were just getting red glow. So you have to keep in mind that a lot of Aurora sightings nowadays are enabled by the fact that we have technology that can capture this. We have advanced satellites in space that allow us to know when we're going to have solar wind conditions and solar storm impacts that are conducive for creating these ribbons and waves of plasma in our atmosphere, and therefore we have more opportunities to actually capture it. Back in the day, it's just you're out walking around going through the village at night and you see these plasma ribbons up overhead and you're a settler in Iceland or something, right? So it was a lot different back before the modern technological age. So it's not that these Aurora sightings are in these Aurora events, these geomagnetic storms are necessarily getting stronger. It's just that we are more aware of them. And that is one of the problems that is unfolding right now, is that we had the big event yesterday. Almost, it's like a 5% chance that we have, less than that, I'd say 1% chance that we get something really big tonight. It's not looking like that's really all that likely, but the solar wind velocity is extremely fast right now. So that is quite unique. It's at about 1,000 kilometers per second. You don't often see the solar wind that fast. Here we can see a graphic kind of showing that. We see this the magnetic field under a slow solar wind regime, but then we had this coronal mass ejection hit, and that compresses the solar wind simply because the velocity is so high. We're nearing 1,000 kilometers per second at this moment in time, which is quite incredible. And we're starting to get the magnetic field of the solar wind to flip into a configuration where it will connect to Earth's magnetic field. So we are likely to see the second surge in geomagnetic activity, but I wouldn't count on there being tons of Aurora overhead if you're living in Missouri tonight. It's probably going to be confined to Canada, Northern Europe, and higher latitude states if we do get some, though you're certainly welcome to try. And after watching this video, you'll have a better understanding of how to look at this data yourself so you can make an informed decision as to whether you should go out, maybe actually take a little trip somewhere a little darker to do some Aurora hunting, because it is quite fun. And we want to be well educated here, not just listening to people regurgitating old headlines, not basing their science communication off of the latest available information and data. That's what we do here on the channel. I'm your host, Stefan Burns, geophysicist, geologist, space weather guy, cosmic bro, whatever. Just someone interested in what's happening here energetically. I've done the research and all the thought experimentation, everything to really get to know this stuff as best as possible. I present videos almost daily, so please subscribe. Okay, so let's get right into it. We had to spend some time with our real-time solar wind data. This is available through NOAA. There are links to these different web pages, or at least closely related web pages in the video description. For example, here you see products and data. There's a whole bunch of different things, but you'll see under observations, real-time solar wind. That's the one that you want to click if you are interested in this, but I'll put a link for sure, if it's not there already, after the live stream is over. We see our solar storm impact. We were under normal conditions here, and then we had this huge solar storm impact. And here's where people are kind of getting things wrong. And the space weather forecasters who are actual space weather forecasters, or they've been doing this like I have for a while or a long time, they're not fooled by this. It's the people that just jumped into all of a sudden giving you Aurora reports when they're like normally weather forecasters, and now they're giving you the space weather forecast and they have no experience there, that are making these mistakes. So we see this huge jump up there. We had 3 solar storms. Remember that? 1, 2, 3. The first one was weak and slow. The middle one was bigger and stronger and faster. And then the third one was the biggest, the strongest, the fastest. It left the sun at very high velocity. The shock wave from that third storm almost certainly, based off of this data, caught up to the other 2, which were slower, and created this extremely high density plasma shock that we see here. Because we see that the velocity did go up to about 700 kilometers per second in that zone. The density went over to about 100 or so. So it spiked up over 100 for the particles per cubic centimeter right as that shock wave was coming in. This is the magnetic field strength. We see our highest value is 63. I'd have to zoom in to get that. And our lowest field value for the BZ component, which you need to be negative for it to connect to Earth's magnetic field and allow this injection of solar wind and plasma into Earth's plasmasphere environment. That is, it went down to like negative 55, negative 50, 51 right there. So very, very good conditions. And for this to be what we would expect just from the first 2 makes no sense. A field value of 63 for the top and below negative 50 for the southward component, that's a really big impact. For reference, the Gannon storm in 2024 May, that top total field reading was 73 nanotesla. And that was a whole sequence that came in combined. And the southward component readings were also in similar territory as this, even maybe a little bit lower. So I think what happened is that third coronal mass ejection was so fast that the shock wave of it actually caught up and compressed the other 2, creating this disturbance, immediately sending us into a G5 minus geomagnetic storm, which you see right here. Our KP index, a measure of geomagnetic activity, went to 8.67. A value of 9 is a G5 storm that is classified as an extreme storm. A G4 storm is classified as a severe storm. I can show you the classifications really quick. There's some other information on here as well, but here we see minor storms, G1, G2 is moderate, G3 is strong, G4 severe, G5 is extreme. We're likely to see this coming up tonight. I'm pretty confident that we'll get G3 storming. I'm not so confident about G4, but it's definitely possible. I think it's very unlikely we get a G5 storm tonight, which is what a lot of people were calling for. I think that has kind of already come and passed because that solar wind shock wave from the third one caught up to the other 2, compressed it to high density, and then the bulk plasma from that third solar storm impacted a few hours ago. So here we see a coronal mass ejection impact right there. This was at roughly 1830 Universal Time, so about 7 hours ago or so. And we see our solar wind strength was 19 nanotesla, and all of a sudden we see it jump to 35. See how that's like an instantaneous jump right there? That, and I can zoom in on that. So here we see that when you get these immediate jumps, that's a coronal mass ejection impact because it's a completely different regime. If we go back to our 3-day view here, so that was that third solar storm impact. And then we had some issues with the data immediately following that. What we see is that the solar wind velocity has been charging up. So all of a sudden it strengthened to about 800 kilometers per second. Now we're nearly at 1,000 kilometers per second. And the magnetic field is starting to enter into that optimal configuration again. But here's the thing. You see that the strength isn't that high. It's only 16 nanotesla. So it's possible that we get another shock to come in. I can't definitively say that this is the third and final. Perhaps that's the second one, but this is not the first one for sure, because the first solar storm that was launched was definitely not that. It was the weakest of the bunch. It wasn't that. It was just not that exceptional. So this has to be 1 and 2 combined. and then very likely actually compressed even further and pressurized from the shock wave of the third one. So I think this is the bulk plasma of the third one that has come in, and because that was the fastest, we're seeing that well reflected here with our velocity at getting close to 1,000 kilometers per second. So that in general already enhances geomagnetic volatility, very fast solar wind. So we're seeing that we're in a G1 storm right now. This is slowly ramping up, especially as this southward component flips negative. And so if you are interested in the Aurora, that's what you want to watch, is you want to watch this right here. And keep in mind that there's about a 30-minute heads up here as to what happens on Earth. So this has just started to go negative. We see that right in the past, basically 90 minutes there. So you take 30 minutes later, and that's starting to now actually sweep by the Earth, because these measurements are taken 1% of the distance from the Earth to the Sun. So under normal velocities, that's about a 1 hour heads up, but because we're at 1,000 kilometers per second or so, it's about a 30-minute heads up, just approximately. So I don't think we have this epic, super widespread Aurora viewing event that a lot of people are running with and a lot of news outlets picked up on. Because it looks like, based off of this data here and knowing how to analyze this data, that the big event was last night. So I hope you saw some Aurora from that. I thought that was quite incredible. Here we see the impact of that. Like, again, let me show you this impact, because you don't get this sort of thing every day. Here we see our magnetic field. I showed this in the live stream last night. It was under normal conditions, and look at the shockwave impact that came in last night. This tells you that this was something big, and again, likely that combination of the 1 and 2 plus the shockwave from the third compressing it all. Boom! Massive increase. Oh my God, massive increase in the magnetic field volatility across the planet. Here we see our scale going from 0 to 400. Most of this is going off the chart. Some of these magnetic field swings were greater than 1,000 nanotesla. That's very, very strong. So that was a G5 minus storm for the first 3 hours, which you could classify as an extreme geomagnetic storm. Then it went down to severe levels, and then down to strong, moderate, and then we've actually been at minor geomagnetic storming for the past 3 hours. If you go back to our display here, the last KP index print here was a 4.67, which is a minor storm. That's a G1 minus storm. So things have cooled off because the field was in this northward configuration, meaning that most of the plasma was kind of slipping around the planet. So if this had stayed southward the whole time, we would have been in for a much bigger geomagnetic storm. Like, this would have probably stayed at a 7 to 8 level the whole time. But because it flipped northward, things started to cool off. But you see how it increased. Look at that very nicely with that impact and the increase in the velocity. We see that geomagnetic volatility increased again. And now, because it's going southward, I expect that to rise up once more. There's more evidence supportive of this, okay? So it's not just off of that. We see often with our proton flux. So when there's a really big explosion on the sun, it's strong enough to actually accelerate different particles like protons, helium ions, electrons, even heavier ions at times like iron and more oxygen, whatever. There's a whole bunch of things floating around space, all the different elements. It will accelerate them to speeds near the speed of light. So this is relativistic speeds. And the faster they go, the higher energy they are. So we see very clearly with our 7-day view here, the 3 solar explosions that occurred. First one, second one, third one. You see this third one was strong enough to even increase the greater than 500 mega electron volt flux. That's very rare. It triggered a ground level enhancement. I discussed that in detail in last night's live stream. It's a quite rare event where you actually have these particles reaching the surface because there's so many of them and they're so energetic. Normally they get absorbed into the upper atmosphere and they trigger electric currents in the ionosphere and they charge up the global electric circuit and a lot more. So we see 1, 2, 3. What happens is a really strong coronal mass ejection is also sweeping up any particles in space, and at the front of it, it has these very strong electric fields that can also then accelerate particles to relativistic speeds at its bow shock. So we see that increase right there. There has been some flare action, but nothing really that crazy. We see that increase right there could be from when that solar storm impacted, because we look at the timing. it is at 1900, and our real-time solar wind shows that impact came in right around that time. Look at that, 1900, okay? So you see how that solar wind, that coronal mass ejection, when it impacted, that is when all of a sudden that proton flux had that final bump. And then if we go back, what you see is once you start to enter into the body of the coronal mass ejection, the big plasma wave, the plasma blob, whatever you want to call it, this starts to go down. And we're seeing that now. It's going down. So that impact is looking very quite clearly to be the third one. And as a result of it not having really anything left to it, I mean, maybe there's more behind it and things just really strengthened. It's possible, but it's not the most likely outcome. So this is starting to go down now. We can also look at our ACE real-time solar wind. And this is specifically looking at particle flux. And we see how things were increasing from these solar storms, because this will again cause this to increase. And then once it comes in, we see this start to go down. That's typically the sign. You know the coronal mass ejection is getting close when this is going up, 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 up. And when it finally hits that peak, that coronal mass ejection is basically about to impact or impacting. And now we're starting to move back down on this. So that's another sign that we are in this coronal mass ejection from the third big explosion on the sun, from that 5.1 X-class flare, the third coronal mass ejection, the bulk of it, and that is going to increase geomagnetic activity once more on our planet. Here we have our geomagnetic perturbation model, which effectively means what the magnetic field is doing for the globe in different spots. So we can click this and zoom in, and we see that the activity has been increasing, but it's really condensed to these high latitude regions, the northern hemisphere in the Arctic Circle, southern hemisphere Arctic Circle. There's that impact from the high velocity solar storm. That's the biggest X factor here. It's the fact that the solar wind is about 1,000 kilometers per second at this moment in time. So that really can raise up geomagnetic volatility just by itself, even with a fairly nominal magnetic field. The fact that the field is still about 4 times stronger than normal does mean that we could enter into G3, G4 conditions. I would put my money more on G3 conditions, but we'll have to wait and see as the remaining structure of the storm passes by. Here we have our geomagnetic volatility as measured by our HB60 index. So let's check that out. Let's just kind of go here. And so we see again that big shock, a bit of a second wave right there, 1, 2, and then we see now that we're starting to go up again. Here, look at that, the timing 20 to 2100. So that is when we had that initial shock from the third coronal mass ejection come in, creating a spike up to G3 minus conditions. So G3 is a KP index or an HP60 index of 7. You click off a third, that makes it a minus. Or for example, if you're at a 6 and you go up a third, that's a plus for whatever that value is. And then we are starting to go back up again, but we'll see if we go up to levels of 7 or so. I'm not betting on 8. It's possible, but I'm not betting on it. So that's why you have to look at this in real time, understand what the data is telling you, and use that to guide your communication and your expectations, because that's important. Last night was the big event. I don't think tonight's going to be, it's going to be great for some people, especially in the higher latitudes, but I don't think it's going to be nearly as epic as last night. Last night was the big energetic wave. We see our DST index here, another measure of geomagnetic volatility. This will allow us to put this into perspective, what we experienced last night and are experiencing right now. I know this is tiny. Maybe I can put this in a new tab for you so it's a little easier to see. Yes, I can do that. Here we are looking effectively at a measure of Earth's ring current. So Earth has this flow of energy that circles around the equator, made up of protons and electrons, and they have different flow regimes. But what happens during a geomagnetic storm is that the ring current gets enhanced. And actually right before the storm, it weakens. That happens almost every time. You'll see that this goes up, indicating that the ring current is getting weaker. And then we get this big drop in the DST, meaning the ring current got stronger, because that ring current, it's an electric current, produces a magnetic field that is oppositional to Earth's magnetic field, meaning it subtracts away from it, which is why the value goes down. So the ring current strengthened this DST index, which measures that with some equatorial magnetometers and compiles the data and gives us this readout. It shows that drop. It went down to negative 238, which is quite a big drop. But for context, last May with the Gannon storm, which was a long duration G5, this storm that we had last night was 3 hours of G5 minus. So they are definitely leagues apart from each other. That one, the Gannon storm, went down to negative 406 nanotesla. This one went down to negative 238. And you see how it's gone up, and now it's at about negative 100. So the storming is still happening, but not nearly at the severity that it was last night. Last night it was extreme. We can see that with our magnetic field measurements for yesterday, taken from all around the globe. The storm came in basically right at midnight universal time, and you'll see all these different plots have a huge shock for the most part right after midnight. Some of them being quite intense. I mean, look at what happened here. This is Sitka, I believe that's Alaska. And so the magnetic field was just going totally bonkers for this location. Our scale here is 100 nanotesla. So this is way off the charts for this location. And we see other locations are like that as well. Mawson, I don't know exactly where that is. But we see that big pulse right there. Things started to stabilize out, but in general, a lot of volatility for the first 12 hours or so of that geomagnetic storm. And we're going to be getting more over the next 12 hours, but as I said, I don't think it's going to be at the same severity that we saw yesterday. So that is basically the update. Just a little bit more on the Aurora for you. We can look here, and if we're talking about the Aurora, there are different colors that show up, and it's good to kind of know what you're looking at when you see this. Now, last night when I went out, I saw green and I saw red, and it was the green layer was lower, the red layer is higher, and that matches up with the science of what we know, because red Aurora is from when you get oxygen ions that are very excited at elevations above about 150 miles or so, start to really resonate, vibrate, and they give off this red glow because they get really ionized from all the energy, and that gives off this red color. Oxygen that's not as excited, you could say, will be at lower latitudes. It'll give off a green color. These are the two most common colors that you see, but sometimes you'll also see purple. This is meaning that it's kind of reaching deeper down into the atmosphere if you see purple, and often you see purple colors when the aurora is overhead, so you're really in the auroral curl. Then these purples can kind of be pulsing over you. That's from ionized molecular nitrogen. Of course, the atmosphere is made up about 70% nitrogen, and then you sometimes get blue colors below 90 or below 60 miles or about 100 kilometers. So these are the main colors that you see. Sometimes you'll see other colors that are a combination of mixing. Like, for example, you may see pink or you may see orange, sometimes yellow, but generally it's some mixed combination of these that create those off colors. These are the four main colors of the aurora. What you may see tonight if you have good viewing conditions, which is based off of your local weather. If you have clouds, good luck. You're not going to see it probably. You need clear skies for the most part, and also how high up you are in latitude. There were some sightings from the very southern parts of Australia that people commented on YouTube and Twitter. Tons of people posted photos of this on Twitter, also on my community page for my YouTube channel. So if you actually go to my YouTube channel, you go to the community section, you'll see some photos of the aurora there. If you want to check those out, you're not a Twitter person, you don't have a login, I don't blame you. Don't bother creating one. Just go to my community page, at my channel page, at Stefan Burns. You'll see a community tab. People posted there. So that is, there were sightings also in the southern hemisphere, but for the most part, it was the northern hemisphere, and that's where the majority of the landmass is. So here, just kind of want to show you this. This is cool. Here we see Aurora from the International Space Station. And so this gives you a sense of what the Aurora is like from space. You see it's not super, super close. It's up, quite up there in the atmosphere. Here we see the green and there's the red. You see the mixing right there with a little bit of orange in between. But that is clearly that layer up above where the oxygen is very excited, over 150 miles or so, well up in the ionosphere. And then the green is closer to the surface, below 150 miles, but it's also oxygen. So that's what we're breathing in effectively. Though you're not up there breathing in that oxygen. But it shows just the incredible molecular dynamics and the chemistry and the physics of the very things that make up our reality that we rely on. We thank all the trees and algae and plants and plankton for the oxygen that they have graced this planet with, and that has totally changed the geophysical system, right? Because now we get Aurora. Not every planet in our solar system has Aurora. We see Aurora on Jupiter, Saturn, sometimes Uranus and Neptune. Earth is a big one. Maybe Mercury. Mercury has a magnetic field, but there's a lot of bodies, right? There's also Venus. There's Mars. You have all the like Ceres, the dwarf planet in the asteroid belt. You have all the trans-Newtonian objects. Like a lot of things in our solar system, gravitationally rounded bodies, don't necessarily have active energetic systems like we do. Or like some of the other planets do. So it really is quite cool that we have that. Let's go to our 30-minute Aurora model, our forecast here to see kind of what's happening. This is real time. Let's check this out. So here we have our 30-minute forecast for the northern hemisphere. And this is the 24-hour model. So it's going to kind of come around. This was, again, you can look at the time here. There's the time. This is 1500 Universal on the 12th, so it's coming around. It's nighttime for Europe. Europe has been getting a bit of a show, especially these high latitude countries. You see the drop down there though, right? And now it's recharging. That's what's happening right now, according to the model. So let me pause that for you right at that spot. That is where we are, according to this model, at 1:55 Universal Time on the 13th. So everyone in Canada should be seeing something at this point if they have clear skies. But as it relates to the United States, you don't see it going down to Florida, okay? So, I mean, there are some people making some sightings. There's probably been some people commenting on the chat maybe about this. But in general, tonight I don't expect to be nearly as epic as last night. We went through why that is based off of the real-time solar wind. Let's also give our friends in the southern hemisphere a look at what they can expect, though. It's a little bit different because their timing is a little different. For example, it's daytime right now in Australia, down under. So here we see though that auroral curl expanding as that third solar storm impact is coming in. And so if you are living in the very southern tip of South America, you may be seeing this right now. Or if you're one of the 100 researchers in Antarctica, it's actually, you're not going to see it in Antarctica because look, it's near solstice. So they're getting almost no nighttime right now. So it's possible that some people here are seeing this, but in general, I'm not sure that this is going to last long enough for this to go all the way to New Zealand, Australia for their nighttime. Perhaps, but I'm just not confident in that. So that is your space weather update for this geomagnetic storm. It appears to be re-strengthening. The solar wind velocity is very high right now at over 1,000 kilometers per second. And that is going to continue to increase the geomagnetic volatility. We'll go to our real-time solar wind one final time just to give it a look, see what's happening. I guess I switched it from over there because it's always updating. Every few minutes it's coming in. And we see, again, we are now in a G2 storm, right? I started at the G1, now we're at a G2. And we see that this is maintaining a negative configuration of about -12. Field strength is 15. That's 3 times stronger than normal. But again, over here, it went up to 63 at one point. The biggest thing right now is that the velocity is very high at 630 or 937 kilometers per second. So in that 900 to 1,000 kilometer range. So that's the biggest factor for for why there is a geomagnetic storm right now and likely to increase to G3 levels or so. That's probably, I think we're going to see G3. I don't think we're seeing G4 today unless something new comes in or there's a sudden strengthening of this interplanetary magnetic field and it flips negative. Because this right here is what was really significant. I mean, look at this, 57, 54, huge increases in the field strength, 60, that is very rare, 63, that's very rare to see. When the magnetic field of the solar wind or the solar storm, whatever it is, the interplanetary magnetic field strengthens, it pushes in deeper to Earth's magnetic field because it's simply just connecting to deeper parts. So Earth has what's known as the magnetopause, the front of Earth's magnetic field. And I can kind of show you here with this graphic. So here you have the magnetopause, okay? And at the magnetopause, typically the magnetic field strength is about 5 nanotesla because the solar wind strength is normally 5 nanotesla. It's just the location where Earth's magnetic field meets up to the interplanetary magnetic field at equivalent strength. So that's going to be typically at about maybe 5 Earth radii, maybe even like 10 Earth radii, 8 Earth radii out, depending on the solar wind strength. If it's around normal, which is 5, it's going to be at those distances. When it strengthens to 60, right, well, it's going to push in a lot closer because the magnetic field decays via an inverse square law. So if you double the distance, the strength goes down by 4. There are other factors than just that, but that's a pretty simple way of understanding it that gets most of the understanding that you need. So going from 60 to 5 is, you know, there's some distance there. So if all of a sudden the interplanetary magnetic field or the solar wind strength, whatever, has a field strength of 60, it's going to connect in much deeper, and now it's able to inject this plasma in much easier because it's pushed Earth's magnetic field simply as a result of its own inherent strength. But Earth's magnetic field itself is static. It's not like Earth's magnetic field goes away in that location. It's just now the solar wind magnetic field is stronger. That's the main active signal. Earth's magnetic field could be considered noise now, if you understand signal to noise ratios, because it's a static magnetic field, but it's a complex dynamic. So that is why we had such a big event last night, because going up to 63 nanotesla for the total field strength with a very strong connection to Earth's magnetic field really pushed it in, and we simply don't have those dynamics active and in play right now. But what we do have is very fast solar wind. That is coming in. So we do have that going. So that is it for today's video. Thank you all so much for watching. If you'd like to stay up to date with what is happening energetically here on Earth, in our solar system, in the cosmos, then please subscribe to the channel. I'm your guy for that, your Cosmic Bro. Smash that like button to help this channel grow. Here almost every single day, providing you with the latest information based off of all these different data feeds and much more. We are currently watching some spots on the globe for earthquake activity. Japan is under high alert right now because of the unusual earthquake swarming occurring there, very close to the epicenter of the magnitude 9.1 Great Tohoku earthquake. We've also had an earthquake swarm with the island of Crete. So there have been some magnitude 5s and 4s there. That's quite anomalous. But hopefully that just dies out. So I'll keep you up to date on all that and much more if you subscribe to the channel. Thanks for watching. Have a great day. I hope you get to see some Aurora wherever you are. And it was really a magical experience for thousands, perhaps millions of people around the globe last night. So if you missed it, I hope you do get a shot at seeing it tonight. But that is your up-to-date, realistic space weather forecast for you based off of what we know. Wishing you well. Have a great day, and I'll see you all very soon.